So our next topic, as you can see, graphs and equations. A bit of this, if not a lot of this, is a recap of what we saw earlier in the year. But as you've probably noticed already, graphing plays such a big role in this new course they've put together. There's a lot more graphing in it. So we do spend a bit of time making sure we've got the basics under control. But the idea here is solving, well, an inequality. Left-hand side greater than right-hand side, so something greater than another. And one of the simplest ideas is, rather than trying to solve left-hand side is greater than right-hand side, is move the right-hand side over and instead try and solve left-hand side minus right-hand side is greater than 0. Because often it's easier to prove something's always positive or something's always negative. And remember, once you know it's a fact, then you can manipulate it and then prove whatever it is that you want to prove. Now, when we're talking about graphs, that's what I've got here, is that we're talking about critical points. Because when does a graph change from being negative to positive? X-intercepts, asymptotes, things like that. So remember, our function, it will only change from positive to negative at the x-intercept, or if there's some discontinuity in the domain, then it might jump from positive to negative. All right, let's just recap this bracket interval notation. We didn't really use it that much in the preliminary, but it is in the syllabus that we're aware of it. So who knows, come the HSC, they might use this notation, so we probably need to be more aware of it now. We're looking at the HSC course. So a bracket means that the endpoint of the interval is included. A parenthesis means that it's not included, the endpoint. And no, they're not smiley faces. Now, if you've got a bracket at each end of the interval, so both the endpoints are, we call that a closed interval. So all the endpoints are included. Whereas if part of it's open, well, hence the word open, but if part of it's not bracketed, then it's open. So one of the endpoints, or maybe both of the endpoints, is not included. Unbounded means it extends out to infinity. There is no boundary. It just keeps going and keeps going and keeps going. So some examples of all those. X is greater than 5 is how we have our inequality. There it is on the number line. That is open because the boundary point not included there. It's unbounded and it's an interval. So we would write it like that. Infinity, of course, has always got a parenthesis rather than a bracket because you can't ever get to infinity, so you can't include it, if you like. And in set notation, we'd write it like that. So we usually use braces to represent a set. X, the colon means such that. So X such that X is greater than 5. Less than or equal to 6, so something like that. That one is closed because that boundary point now is included. And so that one would have a square bracket on the 6. But the minus infinity, again, would have a parenthesis because we could never actually get to infinity. And set notation, X such that X is less than or equal to 6. Then we have sometimes when we're in between 2 points, but that one's open. It's bounded because we have got boundaries on either end. And so that would, and this is the problem with interval notation. You see something like 4, 6, so easy to confuse that with the coordinate 4, 6. So it's probably why we haven't used it a lot. But we need to be aware, are we talking about a point or are we talking about an interval here? So X such that, X, it's in between 4 and 6. And here, that one's a closed bounded interval, and we'd have square brackets at the end of each one of those. So one included, one not included. So that's just a bounded interval. And do I have a 6th one? Yeah, there we go. And then you might have one where there's 2 sections on there. And so it's a union of 2 different intervals. And so union, the symbol for union is U, strangely enough. So we're combining those two, and then set notation again. We have the inequalities. It's the set that's in between and including 2 and 3, union with the set X is in between 4 and 5. You might remember we also talked about composite functions. Composite functions. So that's when you combine a couple of functions together to create some new function. Now I don't think we used the fog notation before, did we? So there you go. There's another notation for composite. We pretty much use the subbing the gx into the f of x. But another way of doing it is fog. So that O, that open circle in the middle, is saying the composite, and it works that way. So whatever the second one is, we're substituting into the first one. So we're substituting the g into the f. So all right, let's do this example. There's function x and gx. So fog of x, sub the 1 on x squared into the 2x on 4 minus x squared. Let's tidy that up. Denominators, multiply everything by x squared. There we go, we get 2 on 4x squared minus 1. As opposed to the golf, okay, that's where we'll sub function x into g of x. And there we go, 4 minus x squared over 4x squared. So a new notation there for composite functions. Now, why is all this useful? So here's this, well, it's a polynomial, it's a cubic, of course. Sometimes we can use the graph to solve it, but really it's just those critical points, those x-intercepts, that are the key points to be checking. So rather than draw the whole number plane, we might just draw a number line. It's a less than or equal to, so I know those critical points, those boundaries will be included. And it's just a matter of testing to see where we are. So let's sub some numbers in. If I sub in a number smaller than -3, we see that yes, that works. It is less than or equal to 0. If you don't believe me, pick a number that's less than -3. Any number you like. -4. We'll go with -4. -4 minus 1 gives us -5. Square -5, you get?
25.
Very good. -4 plus 3, you
-1.
Oh, he's on fire. Multiply those two numbers together and you get?
-25.
Is that less than 0?
Yeah.
Hence, we show that. Okay. What about in between 1 and -3? What number would you pick?
0.
Of course you would. Easiest number to substitute is 0. And so that one we get -1 squared, which is 1 times 3. So no. And then on the right-hand side, pick a number bigger than 1. 2 is bigger than 1. 2 minus 1 is 1. Square it, we get 1. 2 plus 3 is 5. 1 times 5. And so no. So a lot of people would just anticipate that, oh, hang on, we must be on the outside, or something like that. But if you look at it, think of what the graph actually is. You've got a double root at x minus 1 squared, so it would just be touching the axis. Come down, come back up. So there's our solution. Less than or equal to -3, or of course we could have just that single point, x equals 1. Pronumerals in the denominator. All right, so I'm going to use the idea of let's move everything to the left-hand side. It's a lot easier to show something's always negative, something's positive. Well, let's turn it all into one fraction, and there it is. Now, the beauty of this is when you're dividing two things together, it's the same as when you're multiplying them together. I want something that's less than 0. So then either the top's positive and the bottom's negative, or the other way around. But again, it comes down to when is the top or the bottom equal to 0. So you find these two critical points. So the bottom is equal to 0 at -3. The top's equal to 0 at -13 on 5. The only thing you've got to be careful with here, now in this case it's fine, both of them are not included. But if that was a less than or equal to the sign, we still don't include the -3 because we have a bottom of the fraction can't equal 0. So that will never be there. All right, test a point. Give me a number less than -3.
-4.
You are correct. Now, sub that into -13 minus 5x.
-4, top is 7, bottom is -1.
And so it's very good. Now, here's your challenge. A number in between -3 and -13 on 5.
-2.9.
Excellent. Now sub it in.
-2.9 on the top is still negative. I believe bottom is positive, so it's negative. Wait.
So you think it's included in between?
Right. So the top is 13 minus 5x. 2.9. No, never mind. It's not included because positive and positive.
You're right. It ends up not being included. All right, let's do the easy one. Bigger than minus 13 on 5?
0.
0 would be the logical one to pick. So what do we get? Minus 3, which is... So yeah. Look, what you should find with these simple ones like that, it's like a quadratic inequality. It's either going to be between the 2 points or on the outside of the 2 points. Okay, so 3A, bit of a mixture there of things to look at.